Hello, welcome to today's video. So this is going to be continuation of um, the paper I was reading earlier, and the paper is tabular data. Deep learning is not all you need. So the reason I'm doing this is to basically get better at reading papers and trying to do research without getting distracted. Usually uh, it takes more than like 10 sittings for me to finish a paper properly. This for now, this is my second sitting. I I kind of thought about this like in general, and I guess the more I read papers, the less I have to like start cross-referencing resources, basically trying to understand the background and whatnot. So, for example, this is a paper called Tabular Data Deep Learning is Not All You Need. Basically, the idea of the paper is that uh, firstly, it came out in November of 2021. And the basic idea is that uh, this argument that the authors were making, and that is for a lot of tabular data, uh, the researchers are recommending deep learning based models, and uh, the authors have uh, proved, at least in this paper. I just read the abstract and the first part of the uh, introduction. I don't remember if I completed this or not, but basically they were claiming that uh, XGBoost is better. It performs more accurately. It requires much less training. Much less tuning. I'm not sure about if it requires much less training or whatnot, but I think if I remember right, I kind of watched a 10-minute video by the author, a presentation on this work, and if I remember right, the curve is like it just goes down, it converges faster, and also uh, they also claim that they claim that an ensemble of deep models and XGBoost performs better than uh, just XGBoost. So basically, started reading this, and then it's been a while. I don't really have a lot of experience in traditional machine learning, and but yeah, I've taken online courses and then a machine learning class last fall. Bunch of online courses before, and actual graduate course last fall. And I'm kind of a person who uh, I guess I'm not very. I guess I did not do the justice to my course. I basically picked up the concepts that I wanted to. I studied like random forests, and but my basics for decision trees were not very strong. I tried to get a basic idea of decision trees yesterday. That was the last session, and basically, I will like I've put this in the back burner, and but basically, I will study decision trees sometimes in again. Probably code up some basic decision trees on some example data sets, probably follow a tutorial or something. Uh, Understand cross entropy again, information gain, Gini index, and this like another one I can't remember right now. And also, mm, KL divergence is one thing I never understood, and like I never dove deep into it. Maybe I'll try to pick up that as well sometime. But on the other hand, uh, I should say that I at least need to understand XGBoost basically. I got a basic understanding of ensemble models and bagging. Bagging is a straightforward method, but Boosting seems to be a more complicated method. So I kind of ended it on boosting. It was very late in the night, so I just stopped it. And basically, I'll continue from boosting, try to study boosting in general through the web. And then once I get a basic understanding of boosting, I will jump into this paper. It doesn't seem like a very hard read. It seems like it is intended to be easy read. So that's basically my goal. I mean, this is not a very hard read. It says 13 pages, but you can see the references actually start at ninth page. So basically, this is more like 8.5 pages. A lot of it is this is the data set, and then a table for the data set and table for the results. Uh, but yeah, so it's basically like 8 pages and between 8 and 9 pages. So it's not a hard read; it's an easy read. Should be we should be able to do it fast. So I'm gonna go try to understand XGBoost at least on a basic level. Uh, so I understand XGBoost, not just like the results here, because uh, firstly, XGBoost is probably the most widely used traditional machine learning algorithm. It's more of an approach than an algorithm itself, but uh, it's more like uh, it's like decision trees or random forests. You can do like a bunch of different things with them, and you can build them in a bunch of different ways. So I'm gonna try to understand uh, XGBoost first. So I'm gonna stop yapping and start yapping again, but just about XGBoost. Uh, Not XGBoost. I'm gonna start with boosting and then look into XGBoost. So AWS seems to have an article. These are not very bad articles. So let's read this first. Why is boosting important? Wait, this is where we start. Okay. What is boosting in machine learning? Uh, Boosting is a method used in machine learning to reduce errors in predictive data analysis. Data scientists train machine learning software called machine learning models on labeled dataset to make guesses about unlabeled data. A single machine learning model might make prediction errors depending on the accuracy of the training dataset. For example, if a cat identifying model has been trained only on images of white cats, it may occasionally misidentify a black cat. Boosting tries to overcome this issue by training multiple models sequentially to improve the accuracy of the overall system. So I think here we need to put some emphasis on sequentially, because there are basically two types of ensemble models, and ensemble models are where you're basically using multiple models to train something, and they're basically two types. One is boosting and the other one is bagging. uh, Bagging is where you're basically averaging a bunch of different models, generally speaking a bunch of different uh, random forests. uh, but here we're apparently training them sequentially instead of just averaging them directly. Okay. Why is boosting important? Boosting improves machine learning models' predictive accuracy and performance by converting multiple weak learners into a strong learning model. Uh, Machine learning models can be weak learners or strong learners. Weak learners have low prediction accuracy, similar to random guessing. They are prone to overfitting. That is, they can't classify data that varies too much from their original data set. For example, if you train the model to identify cats as animals with pointed ears, it might fail to recognize a cat whose ears are curled. Uh, Strong learners. Strong learners have a higher prediction accuracy. Boosting converts a system of weak learners into a strong learning system, single strong learning system. Mhm. For example, to identify a cat image, it combines a weak learner that guesses for pointers, and then and another learner that guesses for cat-shaped eyes. Okay. After analyzing the image for pointy ears, then system analyzes it once again for cat-shaped eyes. This improves the system's overall uh, accuracy. Okay, so let's back up a little bit here. Uh, so we were reading some articles yesterday, some I guess on different websites and such as DataCamp and some PowerPoints as well. Some PPTs, and basically, there's a more concrete definition for weak learners here. So, random guessing is basically starting prediction. For example, for binary classification, let's say starting with random weights, right? Uh, or you're randomly classifying something. So you have like a 50 or a 40% accuracy that you're gonna get something right. And that is, let's say, random. And weak learners are something which some uh, l- like models which are a little bit better than random guessing, so they're around 60 to 70%. Now strong learners on the other hand have a higher prediction accuracy. Now I'm not sure what this means because uh, depending on different usually it's models these days for different tasks have gotten really good, so it's around like 85 to 90, and in a lot of cases 99, but if you're talking about novel tasks, it's usually like 85% is good accuracy, I'd say. Okay, so how does boosting work? To understand how boosting works, let's describe how machine learning models make decisions. Although there are many variations in implementation, data scientists often use boosting with decision tree algorithms. Okay, I thought boosting's always used, but I guess it's you could say often here. Decision trees are data structures in machine learning that work by dividing the data set into smaller and smaller subsets based on their features. The idea is that decision trees split up the data repeatedly until there is only one class left. For example, a tree, the tree may ask for a series of yes or no questions and divide the data into categories at every single step. Uh, just checking if my audio is still capturing. Recently, I had some issues where, okay, audio is still working. Anyway, so we all kind of know decision tree here. Boosting ensemble method. Boosting creates an ensemble method by combining several weak decision trees sequentially. It assigns weight to the output of individual trees, then it gives incorrect classification from the first decision tree a higher weight and input to the next tree. Okay. After numerous cycles, the uh, boosting combines these weak rules into a single powerful prediction rule. Okay, yeah, this is basically, I guess the AWS articles are not perfect in the sense that if you're trying to learn something, this is not the best way to learn. They are basically writing this to promote how AWS can generally help you with their uh, products. So I don't think they're doing the best job trying to explain this here. But let's actually give them a benefit of the doubt and read the whole thing. Boosting compared to bagging. Boosting and bagging are two common ensemble methods that, okay. In bagging, okay. Yeah, we kind of already understood this, so I'm going to skip that part. So, how is training done in boosting? The training method depends varying on the type of the boosting process called the boosting algorithm. Okay. However, an algorithm takes the following general steps to train the boosting model. The boosting algorithm assigns equal weight to each data sample. It feeds the data to the first machine model called the base algorithm. The base algorithm makes predictions for each data sample. The boosting algorithm assesses, uh, is that how we pronounce it? Assess. Yes. Okay. Model predictions and increases the weight of samples with a more significant error. It also assigns a weight based on model performance. A model that outputs excellent predictions will have a high amount of influence over the final decision. Okay. Like, I'm really not sure what's happening here, to be honest. Yeah, I think this is not really good. So, at least previously, University of Pennsylvania lectures have been a little good to us, but seems like this is more of a lecture notes, so not good. Okay, I mean, at least this is on, I guess this is the main Dan Roth page, so I guess it is fine. Still, uh, just gonna try to understand this anyway. So, yeah, boosting is a general learning paradigm for putting together a strong learner given a collection, possibly infinite, of weak learners. The original boosting algorithm was proposed by as an answer to theoretical question in back learning. Okay. Okay, so learning theory that defines a mathematical relationship between the number of training samples. Okay, it's more like a, you would say like uh, like a, uh, like a subspace of something, like a subset of machine learning. Anyway, this paper shows that boosting has interesting theoretical implications like the relation between back learnability and compression. Okay, not sure what this is. Sounds like Latin. I don't know. Oh, it's the name of. Oh, it's the name of the author, of course. Thought it was Latin. Anyway, this paper shows that boosting has interesting theoretical implications, like the relationship between pack learnability and compression. Okay, so if a concept class is efficiently pack learnable, then it is efficiently learnable by an algorithm whose required memory is bounded by a polynomial in n size c and log 1 by I forgot what this looks like. Uh, looks like belongs to. Not sure. Yeah, let's see. Greek alphabet. Is it epsilon? I think it's epsilon. Guess it's epsilon. I'm not sure, but that's that. So I guess there is a lot of prerequisite knowledge here to read this document right here, but let's be quick. Key contribution of boosting, however, has been in providing a practical way to compose a strong learner from multiple weak learners. In fact, boosting is a member of family of ensemble algorithms, but has stronger guarantees. Mhm. Boosting can be viewed in the context of chatbots. In the early 1990s, AT&T had a chatbot system such that calling a number and answering a set of automated questions would enable the system to navigate you to the right recipient. Goal automatically categorize the type of the call requested by a phone customer. I'd like to place a collect call long distance, please. Collect. Operator, I need to make a call, but I need to bill it to my office. Third number. I'd like to place a call on my MasterCard, please. Calling card. Uh, yeah, 90s stuff. I was in pawn, so I don't know. It is easy to find rules of thumb that are often correct. Example, if the utterance contains card, predict calling card. However, it is hard to find a single highly accurate prediction rule. Therefore, we want an algorithm that can generate a strong learner from a set of weak learners. Procedure: select a small subset of examples, derive a rough rule of thumb, examine and second set of examples, derive a rule of thumb, second rule of thumb, repeat t times, combine learned rules of thumbs into a single hypothesis. 1.3 Theoretical Modification. We define a strong pack algorithm to be for any distribution for any epsilon and delta greater than zero. Okay, Oh, are these like the mean and variance? Yeah, this is the central limit theorem. Because generally, mu is used for the mean, the sample mean, and I don't remember what's variance here, but yeah. Okay, the variance is this sigma, I think. Anyway, given a polynomially many random examples, an algorithm that finds hypothesis with an error less than equal to, I guess this is the sigma, with the probability greater than equal to 1 minus delta. We can also define a weak pack algorithm as one as above, except for between epsilon is less than equal to half minus gamma. In this case, epsilon is not required to be small, to be as small as we want. Instead, it is only bounded by the notation that it predicts correctly more than it predicts incorrectly. Okay. So basically, this is the error. So I guess like the variance could be called the error here, at least in terms of thinking. So that needs to be less than 50%. So Kearns and Valiant uh, asked the question, does weak learnability imply strong learnability? In other words, can we boost from weak to strong? Interesting. Oh, history. I mean, I love that they're teaching it like this here. I'm a story guy. Like, stories make sense to me, not math. So, first probable boosting algorithm. Can weak learner call weak learner three times on three more defined distributions? Okay. Okay. I guess audio is working. Uh, so, Back to the history. How do I say this, man? Like, oof, I'm gonna read it as Freud, but it's wrong. I guess I should just like watch some
Mush.
Josh Strummer videos. This guy's legendary.
Hello.
Mm, so, coding ChatGPT like transformer from scratch. Okay, interesting. Anyway, what we're looking for boosting. I mean, he has a four-part series, so it's not really like the most simple concept in machine learning. Anyway, yeah. First pupil boosting algorithm call weak learner three times on three modified distributions. Get slight boost in accuracy, then apply recursively. Okay. Three modified distributions. Slight boost in accuracy, then yeah. Yeah, let's go through this quickly and look at the formal definitions or like formal view. Optimal algorithm that boosts by majority. First experiments using boosted, limited by practical drawbacks. Introduced ADA boost. Algorithm has strong practical advantages over previous boosting algorithms. Okay, so the formal view of boosting, given a training set x to y, uh, labels go from -1 to +1, the correct label of the instance xi for t in 1 to t. Construct a distribution dt on 0 1 to m. Okay, so these are like, I think this here, yeah, repeat t times. So that makes sense. So it's basically like you do this step again and again. Construct a distribution, find a weak hypothesis, rule of thumb, htx with a small error on dt, cool. That doesn't make any sense, but let's move forward. Typically, when people talk about boosting, they are referring to ADA boost. In ADA boost, the basic procedure requires choosing distribution over the data, learning a weak hypothesis based on the data as drawn from that distribution, and choosing a new distribution. Such as mistakes are weighted more heavily, from which a new weak hypothesis can be learned, where this process can be repeated for any arbitrary number of weak learners. To begin, the first distribution D1, where D1 of the I is the weight of the ith example is uniform. Now, for any arbitrary time t, we can compute the next distribution dt plus 1 given the current distribution dt and the hypothesis ht. like e power negative alpha of t yi ht of x. Is this the learning rate? Okay, alpha of t is given by half of log uh, of 1 minus. Okay, not sure what this is. Hmm, it's so funny because this just looks like the belongs to symbol. Okay, so this epsilon is this is the sum of the y is the ground truth value ta tag of the target variable. So this is like so this is where it's either plus one or minus one, right? So since it's plus one or minus one, we have like weight, let's say it's like 0.5 at the start, or like supposed to be better than 0.5, or whatever it is. And Km is like, oh yes, sure, it's the hypothesis. Yeah, I'm just gonna like watch Josh Thomas video honestly and come back to this.